Colleagues, good day and welcome to the Moscow Telecommunications Seminar. Our today's speaker is Kirill Glinskiy. Kirill is currently pursuing his PhD under the supervision of Evgeny Korov. Kirill received his master's degree with honors in applied mathematics and physics from Moscow Institute of Physics and Technology 2 years ago. He is currently a researcher at the Wireless Networks Lab of the Institute for Information Transmission Problems. And his research interests include the application of machine learning in wireless networks and testbeds. Today he will present us his recent results on 3D printing technology usage for wireless networks prototyping. Kirill, the floor is yours.
Yeah, thank you, Vyacheslav. Yes, today I would like to give a talk on the use of additive manufacturing or rapid prototyping of passive and active radio frequency components for wireless networks. And the plan that I'm going to here today is as follows. First, I would like to give a short intro of additive manufacturing. It's a broad concept. Then I'm going to follow it with a description of most common materials and methods for each type of additive manufacturing. Give a short, concise summary of what has been already done in this field. And finally, I'd like to follow it up with my personal experience with 3D printing of radio frequency components in the form of few practical cases. Which advantages and which challenges have we faced and overcome in regards to rapid manufacturing of waveguides, of radio frequency lenses, and our current research of 3D printed reconfigurable intelligent surface cells, which are active elements. So let us dive in the additive manufacturing itself. So the additive manufacturing is a method of fabricating material objects, details, components, layer by layer. So opposing to the conventional subtractive manufacturing, where we start with a large slab of material, which we can drill, we can cut it, and we remove material from it. We instead build it layer by layer with some sort of machine, for example, which is often called a 3D printer. There are lots of advantages to this approach. It has much less waste, as we use only the material we require. It has significantly less limitations for workpiece. For example, we can build a hollow object inside, which would be impossible with conventional subtractive manufacturing. And we have much less strict geometry constraints. So again, we can build something with a lot of overhangs, a lot of like lattices with variable infill, and all of those advantages. However, this method is slower, as we can remove material much faster than we add it. And generally speaking, if you're speaking about the weight of the finished detail, this technology will be more expensive than mass-produced technology like molding or machining. However, for prototyping, those disadvantages are not so pronounced, as we still we do not need large amounts of details at this stage. The additive manufacturing is, of course, a very broad term for multiple types of 3D printing with various technologies contained in it. Let us now work over them in greater detail. Here are a list of 5, I'd say, most prominent methods for additive manufacturing. So those are called fused deposition, stereolithography, selective and direct metal laser sintering, and the so-called material jetting printing. All of these technologies are quite old, ranging from even 1980s, but they have been recently reinvigorated with the popularization of prototyping for the novel techniques and the overall reductions in costs of many 3D printing approaches. So I would like to start with the most popular and well-known one. This one is called fused deposition modeling, and it's probably the one you think about when somebody calls something 3D printed. So it's an extrusion-based process where we have a long line of filaments for polymer material, which is spun onto a spool, and then is extruded through a heated nozzle. to then print the material layer by layer. So we extrude thin line of material and layer by layer complete detail. It's probably the cheapest one, with printers costing below a few hundreds of dollars and filaments a few dollars per kilogram. It's quite fast, and with multiple models, which are already with 3D printers with multiple models already common, it's even possible to print with multiple material. For example, different colors of plastics, or one soluble plastic and another one is not soluble. So we can just then dissolve the supports. And with this large of varied property polymers, one can print some very tough details. Other would be elastic. Some of them will be filled with glass or glitter to improve other properties. However, it has some disadvantages. The first of all is that as we are printing with polymers and we need to melt them to extrude, that means that our thermal resistance is limited. So, for example, those details cannot be soldered in an oven, and their thermal performance is limited by the fact that they melt. Also, the size of the nozzle it determines not only the speed with which we can extrude the polymer, but also the size of the smaller detail we can resolve. And as we can see, we cannot print sizing on thin air. We need some sort of support. So printing overhangs is a little bit more complicated and is usually done with supports, some sort of detachable plastic guards or rails, or with dissolvable support, so we can just fill the rest with other soluble material and then dissolve it in water or acetone or any other solvent. Now, to the second most popular, the recently popularized one called stereolithography. This is probably the second cheapest method of 3D printing, owing to the massive reductions in cost of high-powered ultraviolet lasers and projectors. So the main concept behind this 3D printing approach is that we can fill a vat with some liquid resin, which is photosensitive. So it hardens and becomes solid when irradiated with UV light. And with using either the laser or the projector, we can selectively cure or harden some parts of the detail, and then we can raise it a little bit. So the next layer can also be exposed, cured, and so on, so on. So this method can work with very fine details because the laser has a very thin point, very thin beam, and the platform can be raised in very small increments, sizes of tens of micrometers. So that results in much greater resolution and surface quality compared to FDM printers. So, for example, details of up to tens of micrometers can be resolved with SLA, while with FDM printing, only, I'd say, 0.1 or 0.2 millimeters at best. Additionally, with most types of 3D printing where the entire screen of one layer is exposed at the moment, the speed at which we print is limited only by the layer count. So as the entire layer is exposed all by once, that means that we can print as many details as we wish, and only the amount of expositions will limit our printing time. However, it has some disadvantages, mostly mechanical, as the liquid resin is a very specific type of chemical compound. It's generally quite brittle, similar to epoxy resin. And as the object is removed from the vat, it's still covered with non-cured still liquid resin, and it first needs to be washed off, and then we're faced with a detail which is only half covered in sort of semi-liquid resin, where it has not been fully exposed due to the non-ideality of light source, non-ideality of resin itself, and it needs to be post-processed, generally with washing it in ultrasonic bath and then cured with some sort of larger scale UV light, so all around. And these methods, of course, is limited to only single material, as it can as it fills the entire vat, and also is, in that regard, it's quite hard to recharge after the printing has been completed. It means that for another polymer, we would need to drain the resin into, for example, some container and fill it with another one. The laser scattering methods are, in some sense, similar to the previously described stereolithography, in the sense that here we also use the light source to make some part of the detailed solid, and here we can use the laser to sinter either the polymer, in which case it's SLS technology, or direct metal like powders like aluminum or titanium, to harden them and create a fully metal detail. This method has quite very high precision, as laser can be collimated to a very fine point. It creates very strong structures, pretty much equal to the strength to injection molded parts, so parts which are isotropic. And as the object is suspended in bed with powder, which is to be sintered, it means that no need for support is required at all. However, this approach is also limited to single material, and the device, of course, has very high costs. So compared to two previous approaches, which have been cheapened enough for the pretty much desktop use and enthusiast use, this one remains the option only for large companies or other, I'd say, rich companies. The final approach I would like to talk about, it's quite, currently at the moment, it's not quite as often used as the previous one, but is rapidly gaining traction. Here, this one called is multi-jet printing, and is in some sense of a synthesis of two previous approaches of both the FDM and SLA. So the concept here is that we can deposit some material similar to an inkjet printer, except this time it's not an ink, but rather some UV soluble composition. UV hardened composition, similar to the resins in the first one, but instead of being filled in a vat, here we can just extrude a small droplet of this component and then harden it under the UV lamp. So this results in very high accuracy and smooth surface, similar to the quality of inkjet printer, and has the advantage of being able to use multiple materials, just have multiple nozzles. In fact, these materials can be, for example, conductive or dielectric or transparent or any other properties you wish to use. But the disadvantage is the slowest method of them all, as each droplet is very small in size and needs to be hardened. So the speed of printing is many times slower than the stereolithography ones. And the ink, the resin, which is also quite expensive, as it needs to be able to be easily extruded in very small droplets. And of course, this jet structure is quite expensive, as it needs to be very, very precise. And all of these nozzles have to be aligned one to the other, so we do not have defects when changing from one filament to another one. So, in summary, I'd say that each of these additive manufacturing methods has its own merit, and there is no singular best approach for all of the tasks where you would want to use additive manufacturing. So, for example, when we want to go cheapest and fastest, the FDM approach would be the best bet. When we need to be precise while still remaining quite accessible for a larger number of users, we need to use SLA. The strength and metal requirements point us to the laser sintering approaches. And when we need to create something extremely complex, the multi-jet printing probably would be our best bet. Now I would like to go about the second part, which is often neglected when describing the use of additive manufacturing, and that is for many radio frequency components, we need not only the dielectric part, but also the conductive one. For example, metal coating of the antennas, or ground planes of some devices. And that means that our printed detail would need to be metallized, so covered in some conductive material. This material, this surface, would need to fulfill a lot of requirements. The most common one are the follows. So the details need to be sufficiently thick so that the conductor skin effect, so that the electromagnetic fields do not penetrate into the through the conductive metal and go and leak out of the detail. Generally, that is achieved by having thickness of at least a few skin depth at operating frequency. It's generally speaking quite small. For example, at gigahertz level, in most conductors, it's on the orders of micrometers. So just a few micrometers of metal would be sufficient. However, they still need to be there. The method needs to, the surface needs to be highly conductive. Preferably, it has the same conductivity as just bulk metal, copper, aluminum, silver. And finally, the metallization needs to be well adhered to the surface so that it will not break away during use, and preferably it should cover it in a uniform way, even if the structure itself is quite complex. So it has a lot of edges, turns, curves, so preferably it should be uniformly thick. Across a lot of papers regarding the use of radio frequency components in devices, there has been a lot of approaches, namely some sort of plating, coatings, and finally, I call them macro scale covers. Those are the use of just simple foil and the use of conductive filaments, which have the metal parts in them altogether. So let us now go over them in greater detail. So probably the most used one conventionally are the platings, namely the electroplating and the electroless plating, which both are used to cover the detail with some conductive layer. Generally speaking, those are copper layers, as copper has quite high conductivity, is common and cheap, and can be easily post-processed with something like sanding papers or polished. The electroplating one uses electrolysis to coat the conductor with some metal ions. So that means that it has the surface needs to be already at least semiconductive. So, for example, often graphite is used for this purpose. Sometimes in the form of graphite mix with something like acetone or oil, and as it requires conductive pre-coating with sufficient coverage, it means that it has some difficulties in achieving intricate patterns. So it's not easy to cover all of the crevices, edges with this preliminary coating. However, after the coating has been already applied, then the process is straightforward. It is submerged into a bath with electrolyte, and the voltage is applied so that the ions can cover it. The metal ions can come to the cathode and coat it. The second one is called, second plating approach is called electroless plating, and as the name implies, it requires some chemical reaction instead of electrolysis to deposit metal on the detail. This one requires no preliminary coating with something conductive. However, it often requires some catalyst or some specific chemical component to cover the object before plating. And that means that the chemicals need to be quite potent. They are often toxic. That means that they are either limited accessibility, limited so in excess, it's not hard to procure, it's hard to procure them, and they can be quite toxic and dangerous and require some special measures when handling them. The other approaches, which I call mechanical ones, require no specific pre-processing, and generally either a vacuum coating or conductive plate coating. So the vacuum coating uses just the acceleration of metal ions via something like ion acceleration to be deposited on substrate in a vacuum chamber. It results in very thin and uniform metal layers, which are, however, generally speaking, quite thick and quite thin, on the order of 1 micrometer or less, which means that they are quite accessible, quite thick enough in terms of skin depth for terahertz, optical, and millimeter components, but for lower frequencies they are insufficient, and that means that it's actually not a great option for our sub-gigahertz or gigahertz level frequencies. The second one, which requires also no chemical pre-processing, is the conductive paint. So the paint can be just made with addition of metal nanoparticles, and when this paint is applied, after the paint solvent dries, that means that a thin metal layer will be formed upon the surface of the printed detail. And this method is quite simple. It's generally speaking low cost and accessible. These paints are often sold on many stores and are quite varied in their parameters. For example, aluminum paints, silver paints, and copper paints are all accessible. However, the disadvantage is that some cheaper sources of paint have much less conductivity. For example, aluminum-based one, due to aluminum oxidation, and this reduced conductivity results in radio frequency performance degradation, as they are not as conductive as bulk metal. Finally, the third group of approaches, I would like to call them macro scale. As compared to previous ones, they can provide much thicker sizes of conductive coverings. So first of all, conductive filaments can be used. Some of them just mix the polymer or resin with metal particles, and after the details are printed, it means that there is metal already inside them, which forms a very good conductive surface. However, those materials are quite costly. As the detail is printed layer by layer, it often introduces the additional roughness, and to print those materials often requires some modified extruders, so some modified nozzles for FDM printing, or modifications for inkjets, so that they can support and not wear reduce the wear from metal particles. And finally, the most obvious and simple one is just to cover the object with some thin metal or aluminum, copper or aluminum foil. It's the simplest one approach, and it's surprisingly quite efficient, especially if the surfaces are quite simple. So they are just straight planes, some lines. However, this process is manual, it's hard to automate it, and it's very time consuming. Naturally, the authors of many papers use pretty much the whole spectrum of both additive manufacturing methods described before and the whole spectrum of metallizing the surfaces described in the previous section. And what do they claim to achieve using these additive manufacturing technology? Generally speaking, there are three types of advantages they want to achieve. Those first are the lightweight of the 3D printed details, as metal is much heavier than plastic. And if we can emulate the structure of metal using just plastic, that means we have huge weight savings. As for example, described in the picture on the right. For example, in this paper, the authors used a 3D printing approach to print a waveguide inside an airplane or UAV wing, so they can reduce the weight of the wing and improve the flight time. Or second approach is to use the advantage that it can make details with some exotic forms. Like, for example, on the left, we can see a specific antenna array, which is a 4x4 antenna array with additional 4 lobes for each of these sub-antennas. Those printing using the multi-jet printing technology. So those conductive antenna elements are placed inside the orange dielectric plastic. And this one offers some advantages in terms of both the bandwidth and the directionality of the antennas. And these performances would be very hard to achieve using conventional manufacturing. It's not possible, in fact, to encase this detail and it's really hard to manufacture it using conventional techniques in terms of the metal devices. Finally, the third one also uses the properties of metal, properties of plastic that the metal does not have. Namely, for example, the picture on second, the picture in the middle demonstrates the use of 3D printing to create an antenna which is usable inside an MRI chamber to monitor the objects under the magnetic resonance measurements. So these magnetic fields will either heat or magnetize the metal antenna, and with its having just a very thin conductive coating, that means that much less heat is produced, and it's simple to use it inside a very strong magnetic field. Of course, those are not the only examples. The field is very dynamically improving. There is a lot of attention going to this the sphere of 3D printing antennas and other antenna elements. But now I would like to give more information about the case studies made at the IATP with regards to our experience in 3D printing some specific components for our research and what we have achieved during this research. So first of all, the part that we have 3D printed and successfully measured is the 3D printed waveguide. So the waveguides are just rectangular conductive boundaries in which the wave can propagate with some specific characteristics like propagation modes and experience much less power loss compared to just the free space propagation. However, while there are a lot of commercial off-the-shelf waveguides available, they have a lot of limits. In particular, they are very high price, named in hundreds of dollars for just a single waveguide. Their dimensions of the waveguides that are commercially available are limited. They have fixed dimensions, which, while they cover the whole radio wave frequencies from 1 gigahertz to up to 200 gigahertz, they still are inapplicable for approaches where we need some specific bandwidth of our waveguide. And finally, they have some material limitations, namely they all are metal, aluminum or copper, and therefore they are heavy, and for some magnetic properties, they are not as applicable. So what was our approach to 3D printing the waveguides? Well, we followed this four-step approach, where first of all we modeled our waveguides in CST Studio to obtain the model of the waveguide and measure its parameters in simulations. After that, after we have finished optimizing the parameters of our waveguide with these parameters such as bandwidth, return loss, some directed parameters, some other relative parameters, we have printed it, we have exported it into CAD software and then to 3D printing software and printed the waveguides using the fused deposition modeling, the FDM technology. After that, so that we have the conductive inner coatings of the waveguides we covered in copper foil, and performed its measurements with the vector network analyzer, which we used to obtain the return loss, which is the amount of power that is returned back due to reflectances inside the waveguide, and fine-tuned the probe length, which is inside this pixel to waveguide transition. So this is just a copper probe from which the waves are radiated, so that it provides minimal return loss across our desired frequency band. The initial results were quite promising. In fact, here you can see a plot of so-called return loss, which means that how much power is radiated back and lost during the transmission. A good value is considered to be below 15 decibels of return loss across the 4.3 to 5.0 gigahertz, and we can see that it satisfies all of those requirements. And as we can see, with the return loss of minus 17 decibels across our required bandwidth, we have achieved similar results to most other waveguides. They are, of course, designed for another frequency, but the standing wave ratio, which can be converted quite simple to the terminals itself, so 9.3 for 17 decibels. We can see that we have achieved the similar results to quite expensive and fully metal waveguides from a well-respected manufacturer. The second device that we have studied during our research was the use of was instead fully dielectric, and it's called Lunenburg lens. In particular, it is a radio frequency lens with its focal distance equal to its radius. So that means that if we apply a spherical wave at the end of the boundary of the lens, that means that on the other side of this lens, we will have a plane wave. That means that that's the key result why it's quite popular to be used in directional antennas in millimeter wave bands, and also to be used as radio reflectors. So those objects that just reflect the signal which is sent to them. So for example, if we covered the lower part of the lens with some conductive material like copper, it would reflect back, and from the falling plane wave, we will receive, from the incident plane wave, we will reflect the plane wave in the same direction. This behavior is achieved by varying the permittivity of the lens, starting from 1 at the boundaries, so similar to air, up to 2 in the center. This design is, with continuous increases in permittivity, is very hard to achieve in real life. And instead, the main approach used was just to build it out of multiple hemispheres with different permittivity values, for example, from different materials, or introduce some perforations to vary the dielectric permittivity. However, the 3D printing has a simple answer to that, and that's called just varying in field. So here we can see on the right the cross section of the 3D printed lens, where we can see that at the beginning we have some very thin lines which fill the lens, and in the center we have much thicker lines, so the infill is much greater in the center, but overall the infill is about 20%, which means that our lens will be 5 times lighter than that of the fully infilled one. And additionally, that means that our lens has significantly less dielectric loss. So a lot of RF materials are lost in terms of that the power is dissipated inside them. Air is a very good dielectric in this regard; it dissipates almost no power. And the greater there is amount of air in the lens, the lesser it dissipates power, and therefore the lesser is its loss. This exotic infill is called gyroid infill, and it was chosen both to ensure the need for no supports in 3D printing, and just to, it has the continuous amount of infill without conflicts. So here you can see the lines that just smoothly go from thinner to thicker ones. Finally, the research that we are currently working on is to use the additive manufacturing in not just simple, fully metallized or fully dielectric components, but rather to implement them in an active radio frequency component, which combines the use of conductive materials, dielectric materials, and some active elements. The elements which can change their state. In particular, what we are aiming for is to recreate the reconfigurable intelligent surface element. So, prominent technology to be used in future networks is to use some arrays of smart surfaces which can change their reflective diagram, so they can steer the signal across some obstacles or focus them at the user. And they need to be both quite cheap in manufacturing, easily scalable. However, at the moment, there are no standardized designs there are no designs that are standard. So that means that we need to prototype a lot of different patterns, a lot of different properties. And so the additive manufacturing will help us to reduce the time per prototype and potentially reduce the cost. So what have we used to make this reconfigurable surface cell? We aimed to use the SLA technology, stereolithography, because of its key advantage of the high temperature of those resins, of the resins used in stereolithography. They can survive soldering with no issues. However, the problem that had presented itself during our study was that while there are a lot of resins with potentially similar mechanical parameters, their electromagnetic properties, be it that permittivity or dielectric loss tangent, are not provided at all. And we cannot obtain them without measurement. Additionally, while there are a lot of standardized approaches to measuring these parameters, they are not suitable for our typical frequencies for the use of RIS. So those methods either aim at lower frequencies, BU up to hundreds of megahertz, and those are the capacitor methods, where we can sandwich the 3D printed material between two flat sheets and measure its capacitance. The probe methods, where we can use the 3D printed detail as a probe for estimating its resonance characteristics, or there are some very high frequency ones where we work at the frequencies of 10 GHz and beyond. So those are the waveguide based one or the resonator based one, where the 3D printed detail is either placed into waveguide or its resonant properties are measured in a way similar to the probe. So what was our approach to this issue? We have created an antenna-based dielectric permittivity measurement approach. We create a set of patch antennas with our 3D printed substrate and some copper foil attached to it, both at the ground plane and at the antenna patch plane. We then measure its resonant characteristics, but not just for one size of patch antenna, but by cutting some part of it, we can obtain second, third, and other iterations of this antenna with different patch sizes, but the same substrate material. So, for example, here we have up to 6, I believe, measurements for which we have all obtained the resonant characteristics and measured their return loss at the resonant peak. After that, we have modeled each of these antennas with different patch sizes in our simulations studio. We have optimized and we have used the optimization tool of the CST to find the material of the patch that would provide the same resonance frequency. So we have fitted the curves from the CST to our experimental data. Finally, we have averaged the parameters of different runs to obtain the final value of permittivity for our specific frequency. Now I would like to talk about the design of the RNS element or unit cell. We have designed the cell specifically so that it has advantages of 3D printing, namely the lower infill, so that it has less dielectric loss. And additionally, this spacer, which is quite thick, but is almost all filled with air, it helps us to expand the frequency band from 20 MHz to up to 200 MHz, which is quite useful for wideband communications. While we do not sacrifice the performance of the cell due to dielectric losses. In particular, we have optimized the infill of the cell so that it has optimal parameters in terms of its phase shift. Its phase shift across on and off states, and after that we have implemented it in 3D printed resin, added the active element, which is pin diode in this case, giving us only two states of the unit cell. And to measure it without creating the full reconfigurable surfaces, we have used the waveguide method, where we have placed the unit cells inside our previously 3D printed waveguide. This was done because these waveguides can recreate the boundary conditions of the periodic reconfigurable surfaces without the need to recreate again the whole surface itself. And we use the vector network analyzer to obtain the power of the reflected signal from rays and the phase shift of the configurable surface itself. So as you can see in the results, for each of the frequency bands from 2.4 to 2.6, sorry, from 2.5 to 2.7, we have obtained difference of less than 20 degrees, which, while sounding quite large, is in fact an excellent fit for the reflector rays, and which results in attenuation of no more than 1 decibel. So our experimental UC will have the performance nearly similar to the potentially ideal one. That brings me to the conclusion of my talk. So the additive manufacturing itself is very buzzwordy and is a very varied family of prototyping methods. Again, there are multiple approaches to creating the dielectric, to the conductive surfaces of those devices. And it means that there is no single method that fits all of them, and therefore the approaches to prototyping their components need to be viewed as a complex of different methods, different steps. So how we can digitally model the specifics of 3D printing, how we can 3D print it, how we can post-process it, and how we can integrate it into the broader communication systems. However, if we achieved those, if we follow these steps correctly, that results in great acceleration in the production of prototype, as they can be done in days, not in months. And also they can have some advantages which were previously considered impossible for the devices. So for example, with variable in fill, we can achieve a single print with varying properties on the inside and on the outside. And that brings me to the end of my talk, and I would like to answer your questions.
Kirill, thank you for your interesting presentation. The first question is from my side. Could you please go to the slide 19?
Yeah, sure.
Here on this slide and on the previous one, you describe the waveguide developed by your colleagues, and here you say that the price of the shelf waveguide with similar parameters is about $1,000. And what is the price of the materials which was used to create your waveguide?
Thank you. It's an excellent question. So this one was printed in very simple cheap plastic, which is, let's say, below $10 per kilogram, and used copper foil with probably a similar price per meter squared. So overall, I'd say it's about 100 times cheaper. If we take probably into account the labor, probably again tens of times of cheaper.
Thank you. The next question is from Alexei Kirill. Can 3D printing be used in industrial manufacturing of RF components?
Yeah, thank you, Alexei. Well, I think that really depends on the amount of objects that need to be manufactured industrially. So, for example, if we're speaking about hundreds or thousands of parts, then I'd say it's still possible to use 3D printing in this industrial process. But if we're talking about probably tens or thousands or tens of thousands of devices, then probably it would be better to look at some other approaches.
Okay, thank you. So am I right that if, for example, we want to product your Lenneberg lens in dozens of thousands amount, it will be impossible? Or there are some 3D printers that are used for this task?
Generally speaking, those when we're talking about scaling 3D printing, we can just buy more printers and hire more people to work with them. So it's quite scalable in that regard. But the problem is that a lot of other technologies become much cheaper at scale. For example, molding, where you just pay once for the form or for the molds, and then just for the machine. Whereas the 3D printing scales, it starts off quite cheap, but then it doesn't get much cheaper after that. So we're talking about the price curves. Probably it would be more expensive, but still possible to manufacture it in thousands compared to the other approach.
Okay, thank you. And I have a next question. So you said that using 3D printing, you can produce very low cost details. For example, for I mentioned waveguide, but you didn't include here the price of a person who create this. And if we consider, for example, like expensive RF components, there are people who produce them, and if there are thousands of them, thousands of details, the overall price of the man will be lower than in 3D printing. No?
Well, probably yes, in some cases. For example, I have mentioned that covering the detail with foil is labor intensive. But for example, using electroplating is only marginally more expensive, but can be done fully automatically. So probably there is a lot of different sub-approaches, even when using 3D printing, that can accommodate the greater or smaller scale. And of course, we are not seeing the full picture by just comparing the price of materials with the price of the complete device. But either way, the difference can be quite significant. And for example, while the labor requires time, we also manufacture it locally. Whereas, for example, for this waveguide, we'll have to wait while it arrives from China or America.
Okay, thank you.
Thank you. The next question probably from me. On this slide, you show return loss, and this is experimentally obtained return loss of the developed waveguide. Am I right?
Yes.
And what is the difference of the simulated waveguide which you simulate in CST and the achieved one? So is the you expect to achieve this return loss and you achieve or in CST Studio you have a very different picture of the return loss?
Yes, we had, in fact, the picture is quite similar in its form. So this is a common feature of those two peaks. Generally, those are because the rectangular structure of the waveguide and the probe itself. So, I believe in our simulations with perfect conductivity and before the correction of the probe, we had the overall characteristic quite similar, but I believe the peak sizes were more equal, and beyond from that, it was otherwise in terms of those like large scale characteristics like return loss and the bandwidth. It was quite similar, but I believe the CC was a bit better in terms of bandwidth.
Okay, thank you. The next question from Ilya Levitsky.
Thank you for your presentation. I have maybe a comment. So as far as I understand, these waveguides are used to test some selected number of RIS elements. So if you have some custom shape of them and some custom sizes, you may not be able to use those that are on the market. Is that right?
Yes, yes. So while the waveguides cover the, in fact, they have overlapping frequencies. However, if we want to use the waveguide as a boundary condition, yes, those that are on the market will not fit. And there are two solutions out of this. The first solution is to first manufacture a smaller or larger wrist cell which fits the waveguide of this lineup. That's the easy way, the coward's way, and a lot of people do that. But we have chosen to use the hard way and measure the cell itself, and therefore we manufactured our own waveguide for this purpose.
Okay, so if the waveguide that is presented on this slide is used purely for testing, again, as far as I understand, we do not need to worry about the mass scale production of these waveguides, right?
Yes.
So the price here is just maybe justified by the developers or the designers of the RIS, but not for the people or companies that will be interested in buying the product that is the reconfigurable surface itself.
Yes, you have a point, but I mean, from the user perspective, you either can pay the $1,000 and have an additional smaller or larger RIS, or you can invest some time and less amount of money to try to obtain the correct, the perfect fitting waveguide, and that probably, yes, it's not a fully determined solution, so it's probably there can be a scenario where the waveguide it's simpler to just buy a waveguide, but otherwise the economics look like it's much cheaper. And also those waveguides often have large lead times, so they have to be shipped. There is a lot of bureaucracy. For example, this one, all of these waveguides are actually export controlled for some reason, I don't know.
Okay, thank you.
Thank you. The next question, I have one question. Could you please go to the slide number 23, I guess? Yes, yeah, here. So here you tell us about the problem that the materials have different electromagnetic properties, and it's not known. So could you, maybe I missed it, how do you solve this problem?
So yes, the problem is indeed that while there are a lot of resins on the market, for most of them the properties are not known, not measured, and the conventional methods that are often proposed to use to measure those properties are, in fact, they're very inconveniently either too low frequency or too high frequency. And to solve this problem, we have used this more complex antenna-based approach, where we manufacture a set of antennas which are very well described by their parameters like substrate size, patch size, length of this line, and therefore they can be easily modeled analytically in CC Studio, and we can perform a curve fitting procedure to obtain the true values of the EM parameters.
Okay, thank you. And maybe the final question from my side. Could you please, so you tell us about a number of examples of the usage of additive manufacturing in ITP by you and colleagues. Could you please tell us which one was produced for the first time, and which examples was taken from some papers or some source and just reproduced?
Yeah, yes, thank you. I will, so out of the three main case studies, the waveguide itself is, well, of course, there has been previous works that have made measured the waveguides. As for the, so it's, we do not claim novelty on the use of 3D printing to manufacture waveguides. For the Lüdenberg lens, they have been printed previously, but they have not used the support less in field. So it's, I guess, technically partly novel, but we don't claim it was just a test of 3D printing approach and more experience. And as for the RSL, here we have we claim novelty that indeed this is the first 3D printed RS element, which also uses the key advantage of 3D printing, like partial in field, and also we use the 3D printed waveguides to measure. So we claim novelty on the use of waveguide for measuring exactly the cell we are planning to use. So other researchers before us has either used the entire RAS for its measurement, or they have created a smaller or larger UC so that they can be measured with standard waveguides.
Okay, thank you. So do you publish these results or going to publish these results?
Well, those results have been published in IEEE Lexicon conference in this year in June, and we are currently working on expanding this work.
Okay, thank you. Do we have any more questions from the audience?
May I have one more?
Yeah.
Yeah, go on.
Okay, so the question is about the elements themselves. So maybe I missed, did you tell anything, did you say anything about the comparison of the, not only the price, but the performance of the elements themselves?
Yes. Just for a moment, I would like to switch to slide. Yes. So this this picture demonstrates the phase shift of depending on frequency in gigahertz. So we have chosen the parameters of the RS to be to work in the phase shift, to work as phase shifter in the range of 200 megahertz, so from 2.5 to 2.7, and we have obtained, generally speaking, a good correspondence. So this RIS would be well, quite efficient in this band with no greater than 1 decibel attenuation. So in that sense, it's as performant as we wanted.
Okay, so the question that I wanted to ask, in fact, as follows: is there any performance benefits of using the 3D printed elements, or the only benefit is just in the cost and the performance is pretty much the same?
Well, in fact, if we compare it to the similarly priced or similarly easy to obtain materials, then this combined air plus polymer spacer is in fact much better in terms of radio frequency losses than just the plain PCB material. So the the not 3D printed one will have greater dielectric losses and will, in that sense, perform worse. I believe the difference would be more than a few decibels, but I need to consult the simulation itself. I have not compared it to the fully in field one.
Okay, I see. Thank you once again.
Thank you. Do we have any more questions? So I guess that's all for today. Thank you, Kirill, for the interesting talk. And see you at the next seminars of the Moscow Telecommunication Center. Goodbye.